Let's finally look at the linearity. Now in this case for this extended integral. And the claim is that the extended integral of c times f plus d times g is equal to what you would expect. For all c and d non-negative and f and g being measurable, non-negative, and yeah, measurable, non-negative. How to prove this now? Now it's not any more difficult when we have worked with this approximation theory. So we choose approximations fn, gn to be simple, positive measurable, such that fn is approximating f and gn is approximating g. Then what? Then we know that then hn defined by c times fn plus d times gn is approximating. Then we know that hn approximates also in a monotone fashion h, which is defined as the limiting thing, c plus c times f d times g. And what then? Then the integral of h by the approximation theorem is the limit of the integrals hn. And then hn, because we have a linearity for simple things, so then this is a simple function, simple function, simple function. We use the linearity for simple functions, so then what happens is that this is the integral of c times fn plus the simple integrals here. Let's see, this is also a simple integral. D mu plus d times the simple integral of gn d mu. And now this one converges to c times the true integral or general integral of f, and so on, same way here. So that's why this limit is equal to c times the integral of f plus d times the integral of g. That's the end of the proof. So the approximation, when you asked, okay, that we have an extension of a concept, so then the extension should kind of inherit the nice properties of the previous thing. And yes, now we see that, yes, it does inherit. So we use the linearity for the simple things, and then we use the approximation. And then with these two things in place, we know that, yes, linearity is inherited for this integral here as well. Does that look feasible to you? Okay, very good. So summary. Summary for today is that we know now how to calculate the integral f d mu for any measure mu. So it doesn't need to be the Lebesgue measure. It can be a counting measure or anything. So a Dirac measure or some combinations of complicated measures. So we know how to calculate this for any measurable f which is non-negative, and we know how to do it and any measure mu and we know that this is we know that this is linear and it's monotone functional. We also know that we can approximate the values of this by first approximating this function using simple functions, and then we can approximate this integral. We also know that we use this concept of the square as a simple integral kind of to build this new integral. And we know that when we look at simple things, so then this matches with the plus. That's why we no more use this square box notation at all. We only use this extended notation because it's the same in the special case. So from now on, we can forget about this. There's no need to have this special notion anymore. We are actually also take out the plus now, because there's no need to distinguish, are we looking at the general positive or just simple? So we will take the plus again as well, and we only denote this for measurable non-negative functions. And this is called, finally, this is called the Lebesgue integral of a non-negative function f with respect to the measure mu. Remember, Lebesgue integral has nothing to do with Lebesgue measure, or maybe a little, but the Lebesgue integral is defined for an arbitrary measure